Welcome to the debate. You know, if the power grid just went completely dark tomorrow, the photos on your wall, the printed books on your shelf, they still exist.
Right, yeah. You just need your eyes and, well, a bit of ambient light to read them.
Exactly. The physical object itself is the message. But the vast majority of our modern world, our medical breakthroughs, government treaties, historical archives, they don't exist in that physical, immediate way.
No, they are trapped as these microscopic magnetic pulses on server racks in massive data centers. Pulses that are, frankly, completely invisible to the human eye.
And completely dependent on a massive, highly fragile stack of technology just to be decoded into something readable.
Which brings us to the core of what we are unpacking today. As our digital universe expands exponentially into the exabyte era, we are facing a massive crisis of digital archiving.
So the central question is this. As our data universe expands, does securing our long-term data provenance require abandoning technological complexity in favor of fundamental simplicity?
And we are drawing on some deep industry research here, including white papers by John Monroe and Brad Johns, insights from internet pioneer Vince Cerf, and digital preservation guidelines from the DPC.
Right. And my stance is yes. To avoid catastrophic data loss, we absolutely must escape the complexity trap by returning to fundamentally simple, physics-based, human-readable storage like the DOTS technology.
Well, and my position is that while fundamental simplicity is a beautiful, philosophical ideal, the sheer crushing scale of the 21st century dataverse means we just have no choice but to embrace complex, actively managed digital infrastructures. Continual data migration isn't a trap, it's an unavoidable operational reality.
Let's unpack this complexity trap right off the bat, because it is the bedrock of why I believe our current archival strategy is effectively a ticking clock.
A ticking clock. That's a bit dramatic, don't you think?
Not at all. In archiving, there is a fundamental axiom. Increasing complexity always leads to an increasing probability of catastrophic failure.
But complexity also leads to unprecedented capability, which we desperately need.
Capability for speed, sure, but definitely not for longevity. When we rely on our current high-complexity architectures, we are talking about layers of proprietary software, rigid climate-controlled server rooms, specific hardware drivers. We are making a massive, dangerous gamble.
A gamble that keeps global commerce running, I would point out.
True. But those that propose complex solutions to digital archiving are asking you to trust that that same complex technology will be around 80 years from now to retrieve the data.
I understand the anxiety around that. I do. It requires a lot of ongoing maintenance.
It is way more than anxiety. It is an existential risk. Ask yourself, if your organization lost its digital storage technology tomorrow, would your organization's legacy be a blank page? Or could a mechanically minded person with a light and a lens still retrieve your precious digital assets?
Okay, that is a highly evocative question, but I look at complexity from a completely different angle. Complexity is not a trap. It is the necessary engine that makes modern society function. Let's look at the hard numbers from John Monroe and Brad Johns. Their research projects that enterprise storage is going to reach tens of zettabytes by 2050.
A zettabyte being a billion terabytes, just for context.
Right, exactly. The scale is almost unfathomable. So, while a simple physical medium you can just hold up to the light is elegant, it's a bit like trying to drain the ocean with a teacup.
I wouldn't call it a teacup.
But the operational reality of global business demands high-speed access, active cloud management, and the continuous systematic migration that modern magnetic and solid-state drives provide. You don't use a bicycle to move a mountain, right? Exabyte-scale data requires complex industrial-scale machinery.
But that reliance on complex, high-speed magnetic media for long-term storage is exactly what internet pioneer Vince Cerf was warning us about.
You're bringing up his concept of a looming digital dark age.
Yes, exactly. His concern isn't just that media degrades physically. It is that bits aren't immortal, independent things. They require a staggering, fragile stack of technological translation.
Sure, if you have a spreadsheet from 1992, and you don't have the specific operating system to read it.
Right. If you lack the specific OS and the specific software driver to interpret those magnetic pulses, the data is just meaningless noise. You are left with invisible ones and zeros.
I completely agree with Surf's premise about software obsolescence. We have all lost an old file to an outdated program. But the enterprise storage industry doesn't just leave critical data sitting on obsolete floppy disks in a basement.
They put it on tapes in a basement.
Very sophisticated tapes. We avoid this dark age through active systematic migration.
Ah, yes, the 3 to 5 year migration cycle, the treadmill.
It is a highly effective treadmill. Let's look at standard LTO tape, linear tape open, which is the workhorse of cold storage today. You don't leave data on Generation 4 tape forever.
Because it degrades.
And because technology improves, you actively migrate it to Generation 6, then later to Generation 8. This is an automated, established process that continuously refreshes the data onto modern media. It explicitly prevents the hardware and software obsolescence that Surf is worried about. We manage the complexity.
You are managing it by running a treadmill that never stops, which leads directly into what Monroe identifies as the economic trap.
The cost of doing business.
Endless migration is a massive, unsustainable drain on global energy and capital expenditure budgets, specifically the capex needed to constantly buy new hardware. Let's look at the sheer physics of moving that data.
It's just a data transfer over high-speed networks. Really, it runs in the background.
But it takes physical time. The drives can only spin so fast. Migrating just 10 petabytes of data from an older LTO tape to a newer one using a single drive takes over a year of continuous running.
Which is exactly why enterprise archives use massive parallel tape libraries with multiple robotic arms, not a single drive.
True, but even with robotics, look at the math at an exabyte scale. By the time you finish migrating a zettabyte of data across a 3 to 5 year cycle, the new tapes you just migrated to are already nearing their end of life.
So you just start the cycle over. It is a known operational expense.
Right. It's like trying to repaint the Golden Gate Bridge, but the bridge is doubling in size every single year. The math of endless migration eventually collapses under its own weight.
It forces archives into a perpetual cycle of buying new media, I'll give you that, and spending exorbitant amounts on strict HVAC climate control to keep the magnetic tapes from degrading.
Exactly. You are throwing perfectly good but obsolete hardware into landfills and paying enormous energy bills to cool data that no one has looked at in a decade.
It is undeniably expensive, and the energy consumption is an ecological challenge. I won't argue there. But you are suggesting we step away from this highly efficient, incredibly dense magnetic ecosystem. So how does DOTS actually solve the scale problem without sacrificing access?
It solves it by fundamentally redefining the physical medium to prioritize century-spanning stability over temporary density. It effectively halts that endless migration cycle.
Okay, break down the physical mechanics for me, because that's where you claim the permanence comes from.
Gladly. DOTS uses a proprietary phase change metal alloy. It is sputtered, which means deposited atom by atom onto an archival polyester base, very similar to mylar.
So it's essentially a metallic film on a highly stable, flexible plastic backing?
Precisely. And here is the crucial distinction, and I really want to emphasize this. When we record data to this tape, a laser does not cut it.
It doesn't physically alter the surface?
No, it does not burn it, and we should never use the word etch when referring to how DOTS records data. It absolutely does not etch into the metal alloy. There's zero physical removal of material.
Interesting. Wait, so if it doesn't etch or burn the metal, how is the data actually written?
The laser simply heats the metal alloy past 160 degrees Celsius.
Wait, just heating it? Doesn't that risk melting the surrounding area and corrupting the adjacent data tracks?
That is the beauty of the specific alloy they use. The heat is incredibly localized and precise. It causes an instant phase change at the molecular level, right at that specific microscopic coordinate.
A phase change?
Yes, it transitions the metal from an amorphous, highly reflective, shiny state to a crystalline, low reflectance, dull state.
I see.
So you are fundamentally changing how the metal bounces light back to a sensor without actually removing any material?
Exactly. Think of it like taking a piece of clear glass and sandblasting a microscopic dot into it so it becomes frosted. Except here, there is no physical removal, so there's no debris to ruin the tape mechanism.
I have to say, these arguments you're making are very compelling. It's essentially a microscopic photograph of binary code.
It literally is, and because it operates comfortably between -9 and 66 degrees Celsius, you entirely eliminate the need for those massive, energy-hungry HVAC systems.
I acknowledge the elegance of a non-magnetic phase change alloy. But let's look at the pragmatism here. You are replacing standard magnetic bits with visual spots. How do we realistically retrieve these microscopic dots in 200 years if the specific dots readers no longer exist?
A perfectly valid question.
Because you criticized complex machinery earlier, but reading microscopic spots at scale requires complex optics and imaging sensors.
Yes, but the difference lies in transparency. The decoding instructions for dots are built into the medium itself. At the very beginning of every single tape, there is what's called the Rosetta leader.
Like the Rosetta Stone.
Precisely. It is human-readable, microfilm-scale text and diagrams. It contains visual instructions and the actual open-source code on how to build a reader from scratch.
So the instructions for the machine are printed on the tape itself?
Yes, as long as humanity have a light source, a lens, and a basic camera sensor, the data is completely recoverable. Diane Vogt O'Connor, the former chief of conservation at the Library of Congress, emphasized this exact philosophy.
That successful long-term preservation requires media where you can literally see the information.
Yes, DOTS guarantees backward compatibility for centuries because a Generation 10 reader can read a Generation 1 tape. It's just taking a picture.
That is conceptually brilliant, I'll admit. But I want to pivot to something the Digital Preservation Coalition, the DPC, has been highlighting recently, which is data authenticity.
Oh, absolutely.
Exactly. In the era of generative AI, seeing is no longer believing. We need proof of provenance.
If we can't trust the archive is useless.
Right. And the industry is actively solving this with software frameworks. Take the Coalition for Content Provenance and Authenticity, or C2PA.
Which relies on cryptographic metadata.
Very complex, cryptographically secure metadata attached directly to the digital files. Yes. They use hashing algorithms to track every single change, establish a secure origin, and guarantee AI provenance. If a pixel is altered by an AI, the cryptography logs it.
That sounds ironclad, until you look at the physical layer underneath it.
What do you mean? We are successfully using complex cryptography to secure our complex data.
But cryptographic metadata is entirely undermined if it sits on rewritable magnetic media.
How so? The hashing algorithm would flag any change immediately. If the file is altered, the hash doesn't match the ledger.
It flags the change, yes, but by then, the original data is already gone. You have an alarm, but no original file to go back to.
Well, you would have backups.
Magnetic media writes data by using a tiny electromagnet to physically flip magnetic domains to point north or south. Those domains are entirely fluid. If an AI bot, malware, or a bad actor accesses that drive, they can simply reorient those magnetic domains silently. The original file's overwritten.
So you're saying the alarm goes off, but the thief has already burned down the house?
Exactly. Adding cryptographic metadata to a rewritable magnetic tape is like putting a mathematically perfect, high-tech digital padlock on a canvas tent.
Ah, I like that analogy. The lock itself is unbreakable, but the wall of the tent is just fabric.
Yes. Anyone with the right access can slice right through the fabric, alter what's inside, and you're left holding a perfectly secure padlock attached to a compromised file. If a file can be altered without a physical trace, it completely loses its value as a true historical record.
I understand the vulnerability of rewritable media. It is inherently malleable. But how does DOTS prevent that physical manipulation?
By being a true WORM medium. Write once, read many. Because the DOTS metal alloy undergoes a chemical, physical phase change, you cannot silently flip a bit back.
It's physically impossible?
Completely. You would have to apply intense heat to the entire tape to destroy it, which leaves a highly obvious physical trace. Furthermore, it's non-magnetic and chemically inert. You simply cannot hack a physical molecular structure over a network connection.
Let's talk about the physical footprint of this, though, because that's where my mountain analogy really hits home. You mentioned earlier that DOTS stores about 20 terabytes on a 12-inch reel.
That is correct for the current specifications.
In a modern enterprise context, a single high-end digital film production or a genomic sequencing run might generate a petabyte of data in a matter of weeks.
Sure.
Storing that on 20 terabyte reels requires a massive physical footprint. You are trading extreme data density, which magnetic media excels at, for this physical immutability.
You are absolutely right about the trade-off. Extreme density sacrifices permanence. But I want to use an analogy straight from the preservation community. You don't take a Formula One race car off-roading.
Because the suspension would shatter, it wasn't built for it.
Right. DOT is not meant to replace solid-state drives or NVMe flash storage for hot data, the data you need to access and rewrite in milliseconds. It is designed to do exactly what complex drives and magnetic tapes fundamentally cannot do.
Which is?
Preserve cold, mission-critical data reliably for centuries without the risk of a single bit flip and without the exorbitant cost of continuous migration.
But I think we have to separate the theoretical ideal of an immutable archive from the practical reality of enterprise IT budgets.
The budgets are exactly why we should switch.
Well, yes, the economic trap of migration is real. Yes, paying for HVAC cooling for sprawling server farms is an ecological challenge, but complex, actively managed storage ecosystems are highly adaptable. If a new, denser magnetic technology emerges in 10 years, we migrate to it, gaining massive efficiency.
But operational flexibility is the exact enemy of archival permanence.
Managed complexity allows us to surf the wave of technological advancement. Locking data into a physical, unalterable medium removes that operational flexibility.
When the intelligence community says they need to store data for the life of the republic, they do not want flexibility. They want absolute guarantees. They want to know that a historical photograph or an essential international treaty cannot be silently rewritten by a generative AI program or corrupted by an EMP.
Are we really designing enterprise storage around the threat of an EMP?
When you're archiving the sum of human knowledge, absolutely. An EMP floods an area with intense electromagnetic energy. Because magnetic drives rely on delicate magnetic fields, an EMP essentially scrambles those fields. It instantly randomizes the microscopic magnetic domains, wiping the data cleanly and irreversibly.
And DOTS survives this?
The DOTS phase change metal alloy is entirely non-magnetic, so it is immune to all of it. Water, petrochemicals, extreme heat. It survives. It is literally data as durable as history itself.
Even if we accept that DOTS is the perfect medium for a subset of critical data, the reality of the market, where we are looking at over 100 exabytes of new digital storage needed just for archiving in the near future, means that magnetic media and complex cloud infrastructures will have to continue shouldering the vast majority of the burden.
They will shoulder the burden of the hot data, certainly. But remember John Monroe's central finding. Up to 80% of all enterprise data globally is cool, cold, or frozen.
Data kept just in case for compliance.
Right, or write once, read never, historical data. Using energy-intensive, highly complex, constantly degrading magnetic media to store frozen data is a profound misallocation of resources. By moving that 80% to a visual phase change medium, you fundamentally alter the economics of global data storage.
Look, I just don't think it's a simple binary choice between switching entirely or staying put. The transition to a fundamentally new physical medium requires building an entirely new hardware ecosystem inside these data centers.
It requires an initial capital expenditure, yes, but when you look at the total cost of ownership, the TCO, the math shifts dramatically.
We've covered a vast amount of ground today, diving deep into the physical mechanisms and the philosophical approaches to archiving. I think it's time we summarize our respective positions.
Fair enough.
I maintain that the digital world will always generate unimaginable, escalating quantities of data. Actively managed, complex systems, despite their economic and energetic burdens, will remain the backbone of how we process and distribute that information globally.
We will innovate our way out of the complexity trap with better management software and denser media, not by retreating from it.
And I synthesize my stance by looking at the hard, undeniable metrics of preservation. When you rigorously evaluate the demands of energy efficiency, true data provenance, immunity to AI manipulation, and freedom from the endless migration cycle, I believe you will come to the conclusion that the only long-term solution proposed out there that meets all of the archival metrics is DOTS.
We are clearly at a crossroads in how we treat our digital heritage. The tension between achieving immense exabyte-scale data density and ensuring guaranteed century-spanning retrieval will undoubtedly define the future of human memory.
Absolutely. We highly encourage our listeners to look deeper into the provided white papers, explore John Munro's market metrics, and read the DPC guidelines to decide for themselves which philosophy will ultimately save our digital history.
Well said.
Because ultimately, we had to ask ourselves what kind of ancestors we want to be. Will we leave future generations a fragile, complex machine they no longer know how to operate? Or will we leave them something they can just hold up to the light?